Welcome back to the Deep Dive. Today we are diving into nuclear power. This is a topic that often feels, incredibly big and maybe a little scary, conjuring up images of Cold War tensions or mushroom clouds. But our mission today is to simplify it, strip away all the technical jargon, and show you the incredible science behind it. We're going to break it down like we're explaining it to an incredibly insightful eighth grader.
It's a journey into extremes, really. We're going to start at the unimaginably small scale of the atom, travel through accidental discoveries in dusty Parisian labs, and end up talking about powering our civilization and exploring the furthest reaches of the solar system.
Wow. Okay, so quite a journey then.
It is, and the knowledge itself, the fundamental power of the atom, is entirely neutral. It's just physics. But understanding the choice of how we apply that knowledge, for abundance or for destruction, that's where the real deep dive lies.
Okay, let's unpack this right from the absolute beginning, at the fundamental building block of everything, the atom.
Right. And this idea, it's ancient. It dates back to a Greek philosopher named Democritus, way back around 460 BC.
Democritus, yeah. And he coined the term atomos, which literally means uncuttable.
And that concept of the uncuttable is essential for appreciating the sheer scale we are dealing with. It gives you a way to sort of wrap your head around just how small these fundamental building blocks truly are.
Let's use an analogy that really captures it. Imagine you have a single grape. We're not eating it. We're slicing it in half with an impossibly sharp knife.
Okay.
Now you slice one of those halves again and again. Just keep going, having the piece again and again. After about a dozen slices, the piece is already smaller than a grain of sand. A dozen more, and you're down to the width of a human hair.
Right.
7 more, and you're the size of a bacterium. And this is really where most people's visualization of smallness just stops.
But you have to keep going. If you persevered until you had halved that grape 80 times, which is an impossible task, of course, you would finally encounter the smallest unit of ordinary matter, the atom. 80 slices to get to the atom? That's incredible.
And here's where the scale gets truly mind-blowing. If you somehow scaled that single grape up to the size of the entire planet Earth, its individual atoms would still only be about grape-sized.
Wow, so the density of matter is it's incredible.
So even the smallest object you can think of, a speck of dust, a tiny hair, contains an unimaginable number of atoms. Your grape, for example, contains as many individual atoms as there are stars in the observable universe.
That is just a mind-bending kind of density.
It is. But Democritus, brilliant as he was for thinking this up millennia ago, was fundamentally wrong about one thing.
Right. His atomos wasn't uncuttable. We can, and eventually did split it.
And that's where the power is hiding.
Yeah.
We got to the atom after 80 slices. But to reach the dense, tiny core, the nucleus, you would need another 45 slices.
Another 45. So that dense kernel is 20,000 times smaller than the atom as a whole. It's the truth behind the saying that the atom is mostly just empty space.
Just an electron cloud surrounding that microscopic nucleus.
And inside that unbelievably dense nucleus is our cast of characters, the protons, which carry a positive electrical charge,
Okay.
and the neutrons, which are electrically neutral. Orbiting way out in that vast, empty cloud are the electrons, carrying the negative charge.
Wait, hold on. If charges repel, and we know they do, how do all those positively charged protons stay jammed in that tiny nucleus? It seems like they should be fighting each other and flying apart instantaneously.
Well, yeah, that's the multi-billion-dollar question, isn't it? The electrical repulsion is absolutely massive in that confined space.
So there must be something else.
They need something far stronger to hold them together, something we call the strong nuclear force. This force acts like atomic superglue, completely overwhelming the electrical repulsion.
And when we find a way to break that superglue,
We release the powerful energy that was used to hold the nucleus intact.
so the strong nuclear force is the secret power source. And the main players in triggering this release are the neutrons.
That's right. Protons define the element. If you have 1 proton, it's hydrogen. 92 protons, it's uranium. But neutrons are the ones that affect the atom's nuclear character.
How so?
Well, atoms of the same element that have differing numbers of neutrons are called isotopes. Most elements in nature are stable, but certain heavy isotopes, particularly ones that are off-kilter and unbalanced with too many or too few neutrons, They hold the key to releasing immense energy.
So these off-kilter atoms, they regain their stability either spontaneously through decay
Which is radioactivity.
or through induced splitting, which is what we call fission.
Exactly.
The story of unlocking this inherent atomic energy actually begins with a total accident. We're in Paris in 1896. We're dealing with a physicist named Henri Becquerel.
Right, and he was looking into phosphorescence, this eerie quality of certain substances to absorb sunlight and then slowly radiate it back as a visible glow.
So his hypothesis was that uranium absorbed sunlight and then re-emitted invisible rays.
Exactly, rays that were powerful enough to expose photographic film, even if the film was shielded with opaque paper. It was a logical idea for the time.
So he set up his experiment. He wrapped a photographic plate in thick black paper to keep it dark, sprinkled some uranium salt crystals on top, and waited for the sun.
But the weather did not cooperate. Classic Paris. It was overcast. Thursday, Friday, Saturday, still cloudy and gray.
So, defeated by the French weather, he just terminates the experiment.
Yep, he stored the entire assembly, the paper, the uranium, the photographic plate, in the darkness of a bureau drawer. He expected nothing to happen.
By Sunday, his patience was shot. He decided to develop the photograph anyway, just in case, fully expecting a blank plate because the uranium never got its dose of sunlight.
And when he pulled the plate out of the chemical bath, there it was, a ghostly, clear image of the uranium crystals. The answer was inescapable, and it shook the foundation of physics. The energy wasn't coming from the sun. It was inherent in the uranium atoms themselves, radiating from the nucleus in the dark. That was the accidental discovery of radioactivity.
And the scientific community immediately jumped on this discovery. Within 2 years, Marie Curie and her husband Pierre followed up on Becquerel's work.
Right, they were attempting to isolate the source of this incredible energy emanating from uranium ore. They worked with tons of pitchblende ore, painstakingly extracting and purifying the radioactive components.
And this led to the discovery of 2 entirely new, highly radioactive elements.
Polonium, which was named after Marie's homeland, Poland, and radium, element number 88. Radium was so intensely radioactive that it actually glowed in the dark with an internal ethereal light.
So they named it after the Latin radius, meaning ray of light.
Exactly. And when these unstable off-kilter atoms achieve stability, they spontaneously decay, radiating energy that we often describe like atomic-scale artillery.
Atomic-scale artillery. I like that. Ernest Rutherford, working a few years later, classified this radiation based on how easily it could penetrate matter.
And this is absolutely critical for understanding radiation safety and shielding. He categorized them into 3 main types. First up, you have alpha particles.
Right. Think of alpha particles as heavy, slow cannonballs. They are bulky clusters made of 2 protons and 2 neutrons stuck together.
Because they are so bulky and have a strong positive charge, they interact violently with whatever matter they hit. They lose their energy incredibly quickly.
So a thin sheet of paper blocks them completely.
Completely. Even the top dead layer of your skin, or just a few inches of air, is enough to stop an intense stream of alpha particles dead in its tracks. They are highly dangerous if you inhale or ingest them, because then they'd fire their cannonballs directly into sensitive internal tissues.
Okay, so that's the cannonball. Next up are the beta particles.
These are much lighter, zippier electrons, more like high-velocity bullets approaching the speed of light.
So they're energetic, but they dissipate their energy over a much wider area than the heavy alpha particles.
Right. Beta particles can travel several meters through the air. They will penetrate the skin, causing damage, but typically won't go much deeper than that. You need a slightly thicker layer of material to stop them, something like thick plastic or a thin sheet of aluminum.
And the fascinating part of beta decay is the transmutation. A neutron inside the nucleus spontaneously turns into a proton.
And fires out a beta particle, which is an electron.
So because it gains a proton, the atom changes its identity, moving 1 space up the periodic table.
Precisely. For example, naturally occurring radioactive potassium, element number 19, beta decays into stable calcium, element number 20.
Which is why things like grapes, bananas, potatoes, and even the concrete in your walls are slightly radioactive. It's all that potassium-40.
Exactly. And finally, you have the gamma rays.
These aren't particles at all, are they?
No, they're pure energy individual flashes of invisible light traveling at the speed of light. Gamma radiation is only stopped by a direct head-on collision with an atom's nucleus.
And since we already established that atoms are mostly just empty space.
Gamma rays usually shine right through matter with ease. They are highly penetrating. To block them, you need sheer density and mass. thick walls of lead or dense concrete. They are like a highly energetic yawn the atom makes to get rid of excess energy.
So that entire process is spontaneous decay nature finding balance. But the real story of power generation is about forcing the atom to split.
Right, which is fission.
So if the goal is to intentionally change the nature of an atom, we're talking about achieving the ancient alchemist dream, transmutation.
Turning one element into another. And the first person to truly achieve this was Ernest Rutherford in 1919. He became the father of nuclear physics by shooting nitrogen atoms with heavy alpha particles.
Smashing those cannonballs into the nucleus of nitrogen, he was literally chipping away at the block.
He was. And 6 years later, his student Patrick Blackett analyzed the results and found the crucial piece of the puzzle. The alpha particle didn't just ricochet off the nitrogen nucleus, it merged with it.
So nitrogen is element number 7. Adding the 2 protons from the alpha particle makes 9, then losing 1 proton in the resulting blast takes it back to 8.
Oxygen. They had transformed nitrogen into oxygen.
That's why nuclear reactions are so profoundly different from chemical reactions. When you burn methane, you just reshuffle the atoms. The carbon remains carbon. But here, they fundamentally changed the element itself.
At will, yeah. The key difficulty, though, was firing those charged alpha particles into a positively charged nucleus. It's like trying to push 2 positive ends of strong magnets together.
They just repel each other. It's incredibly hard to hit the target.
Exactly. And that obstacle brings us to Enrico Fermi, the brilliant Italian physicist. In 1934, he found the workaround, the easier way in, using neutrons.
Because neutrons are neutral, they sail right towards the charged nucleus unperturbed by electrical forces.
They are the perfect frictionless spark plug. So Fermi began bombarding uranium, element 92, with these neutral neutrons, hoping to create elements heavier than uranium. He did create new isotopes, but he couldn't quite figure out what he had made.
The actual world-changing moment of fission arrived 4 years later with chemists Otto Hahn and Fritz Strassmann in Germany.
When they repeated Fermi's experiments and analyzed the results, they found barium, element number 56.
An enormous difference of 36 protons from the starting uranium atom. That must have seemed impossible.
It did. The scientific community thought it was impossible. Nuclear forces were supposed to be too strong to knock off more than a couple of protons at a time. This didn't make any sense.
So who solved the riddle?
It was Lise Meitner and her nephew Otto Frisch who were working on this problem over Christmas 1938. They realized the uranium nucleus was so massive that the mutual electrical repulsion between all those 92 protons,
Which was normally contained by the strong nuclear glue.
could overcome the glue and cause the entire nucleus to snap in two when hit by a neutron.
This snapping in two is called fission. They use the analogy of the nucleus as a wobbling drop of water.
Right. When the neutron spark hits it, the internal electrical repulsion causes the drop to oscillate until it elongates and splits into 2 smaller, highly energetic fragments like barium and krypton. And these fragments rocket away from each other at incredible speeds.
Which is where we link back to Einstein's famous equation EMC-Phi. Where does all that explosive energy come from?
We use the vintage weighing scales analogy. Imagine we could perfectly measure the mass if you put a single uranium atom on one pan of the scale.
And the 2 fission fragments plus the expelled neutrons on the other pan.
The uranium atom would be heavier. A tiny bit of mass has vanished.
That tiny missing mass wasn't truly missing. It was converted entirely into energy.
And the exchange rate for this conversion is c the speed of light squared. And this rate is absolutely enormous. The speed of light is about 300 million meters per second. Squaring that number gives you 90 quadrillion.
Wow. So if you take even the smallest, most microscopic amount of mass and multiply it by 90 quadrillion, you generate a monumental amount of energy.
That's why nuclear fuel is in a class of its own compared to chemical fuels. The sheer scale of energy released is staggering.
Give us some context.
1 single gram of uranium releases as much energy as burning over a ton of high-quality coal. To put it another way, if you powered a typical light bulb using a single gram of coal, you'd get less than 15 minutes of light.
Okay. And with uranium.
But if you used 1 gram of uranium, you could power that light bulb for about 30 years straight. The energy density is revolutionary.
So we know how one atom splits, but a nuclear reactor needs more than just one split. It needs a self-sustaining process.
Right. And when uranium atoms split, they don't just blast out the 2 fission fragments, they also expel 2 or 3 new neutrons, which are those crucial loose neutron sparks.
And in the presence of more fissile uranium atoms, those loose neutrons are like flint sparks in a haystack.
One spark hits an atom, splits it, releases more sparks, and those sparks hit more atoms, sustaining the reaction indefinitely. This is the fission chain reaction.
The crucial challenge, then, is controlling this runaway loop of positive feedback.
Right. The key metric developed to track this is the K value, which is the average number of neutrons from one fission that go on to spark another. This K value dictates the fate of the reaction.
So if K is less than 1,
The chain reaction gradually dies out. It's subcritical, ending with a whimper.
and if K is greater than 1,
The number of fissions escalates exponentially. That's supercriticality, ending with a bang. For example, if K2, the fissions double every microsecond, 1 becomes 2, then 4, 8, 16. After just 40 links, you have over 1 trillion fissions.
that's how atomic bombs work, an uncontrolled, rapid release of energy.
But the goal of nuclear power is the Goldilocks zone. If K equals exactly 1, each fission sparks exactly one other, maintaining a steady, controlled burn indefinitely. This is called criticality.
And the challenge in 1942 was proving that a controlled critical reaction was even possible.
Which brings us back to Enrico Fermi, now in the USA as a refugee from Mussolini, leading the effort to achieve the first controlled chain reaction.
And this legendary experiment took place in, of all places, an old squash court beneath the spectator stands of the University of Chicago's football field.
It's incredible. The reactor, nicknamed Chicago Pile 1, was utterly homemade. Construction began in November 1942. It was grueling work. The goal was to build a lattice structure where uranium was interspersed with graphite blocks.
And the graphite was to slow the neutrons down.
Exactly. They stacked thousands of slippery 10-kilogram graphite blocks by hand, alternating layers of pure graphite with layers containing uranium slugs. They were literally inventing the field as they went.
And given the stakes, they were handling enough fissionable material to cause a devastating reaction in the middle of a major city. They needed a bulletproof safety plan.
Absolutely. They used what are called neutron poisons, elements that simply absorb neutrons, effectively severing the chain reaction instantly. Their poison of choice was cadmium.
And the initial safety system was incredibly rustic.
Oh, it was. The cadmium was nailed in sheets to 12-foot wooden planks, which were pushed into horizontal slots in the graphite by hand to manually control the flow of neutrons.
So what was the backup plan?
They did have an automatic safety system. Poison planks suspended by rope that would drop automatically if the neutron count spiked. But the backup to that was a physicist, Norman Hilberry, who stood ready with a fire axe.
A fire
A
axe.
fire axe. He was told to cut the rope instantly if the automatic systems failed.
And there's a backup to the backup.
The final backup. A 3-person suicide squad standing ready on a platform above the reactor with buckets of cadmium solution, prepared to pour the poison onto the pile if everything else went wrong.
That is the most terrifying job description I've ever heard.
The tension on December 2nd, 1942 must have been palpable. Fermi called out instructions inch by inch to remove the cadmium planks. George Weil slid the final plank, nicknamed Zip, out of the reactor.
The neutron counters went from a regular clicking rhythm to a frenzied, accelerating swarm.
Everything unfolded exactly as Fermi had predicted. The moment of triumph arrived. The pile has gone critical. It was 11 minutes to 4 in the afternoon.
Dawn of the atomic age.
Yeah.
And how much power did it generate?
Half a watt, barely enough to flicker a light bulb. Fermi shut it down just 4 minutes later, knowing that left uncontrolled, it would climb to 1 billion watts, killing everyone in the vicinity.
It's such a profound historical moment. Humanity had reached a forked road.
They had controlled the release of nuclear energy, and the key takeaway is the difference between an atomic bomb and a nuclear reactor. A bomb is an uncontrolled, rapid release of energy. A reactor is an orchestration, a careful, steady burn for peaceful civilization.
Comparing them is like comparing a high explosive to a tea light candle.
Exactly.
So we proved the fire could be controlled with half a watt of power in that dusty squash court. How did we scale that incredibly rustic 1942 experiment into a massive industrial machine that powers a city?
That's the leap to modern nuclear power stations. When we look at them today, we are fundamentally looking at a very sophisticated way to boil water.
It all comes down to boiling water.
The core function remains simple. Generate heat inside the reactor by splitting atoms, use that heat to boil water into steam, and the steam drives a turbine to make electricity.
And the fuel starts as jet black uranium dioxide powder.
Right. This powder is pressed into grape-sized ceramic pellets. And the potency of a single pellet is astonishing. One ceramic pellet can generate as much electricity as burning a ton of coal.
Those pellets are then stacked inside long, thin metal tubes called fuel rods.
Typically 3 to 4 meters long, made of a zirconium alloy, which is chemically inert and designed to allow the loose neutron sparks to pass through easily. These rods are then bundled together to form the reactor core.
And the most common industrial reactor today is the pressurized water reactor, or PWR.
Right. This design relies heavily on water for two crucial jobs. First, it's the coolant, drawing the immense heat away from the incredibly hot fuel rods.
And second, the water acts as the moderator.
Exactly. Remember those newborn neutrons blasted out during fission travel at breakneck speed? They are too fast to be easily captured by another uranium atom.
So they're unlikely to cause a new fission.
Right. The water molecules slow them down dramatically, turning them into thermal neutrons, which are much more likely to sustain the chain reaction.
So in a PWR, the water is heated by the core to over 300 degrees Celsius. But they keep it under immense pressure to prevent it from boiling inside the reactor.
About 155 times atmospheric pressure. It stays liquid, which is crucial for its job as a moderator. It is essentially a giant high-pressure teapot.
But the true stroke of genius, the reason these reactors are so safe, is their intrinsic self-regulating mechanism.
The negative temperature coefficient. It works like a perfect thermostat, ensuring the reactor can't run away.
So if the core starts to get too hot, meaning the rate of fission is increasing.
The water itself expands. When water expands, it becomes less dense and therefore a worse moderator. Fewer neutrons are slowed down to the optimal thermal speed, the chain reaction slows, and the core automatically cools down.
This is negative feedback in action. Heat cannot soar out of control.
It can't. And when the reactor cools, the water contracts, allowing more neutrons to be slowed, and the reaction speeds up again to maintain the temperature. It is a brilliant piece of physics design that guarantees stability.
However, using regular or light water as a moderator presents a challenge linked to the fuel composition.
It does. Natural uranium is 99.3% uranium-238, which doesn't split easily. Only 0.7% is U-235, the valuable fissile isotope.
And light water is such a strong moderator that if you use natural uranium, the chain reaction simply won't start.
The water quenches too many neutrons too quickly. The simple fix, employed in most reactors globally, is to increase the ratio of U-235 to about 5%. This is called enrichment.
And it massively increases the fuel's potency. The process of enrichment is a feat of engineering itself.
It really is. First, the uranium is converted into a gas called hex-uranium hexafluoride.
This hex gas is then puffed into vertical cylinders, often compared to the pipes of a large church organ.
These pipes, called centrifuges, are spun at truly incredible speeds, up to 60,000 revolutions per minute. The internal wall of the cylinder generates up to 400,000 times the force of gravity.
That's insane. And that speed is necessary because U-238 is only slightly heavier than U-235?
Just slightly. In that powerful spin cycle, the heavier U-238 hex is squished fractionally more towards the outside wall, and the slightly lighter U-235 hex is muscled towards the center.
The lighter U-235 rich gas is then tapped off and run through the process again and again in a cascade until it reaches that 5% potency.
Once enriched, it's stripped of the fluorine and pressed into those fuel pellets. The leftover material with diminished U-235 is called depleted uranium, or hextale.
And we have a vast global stockpile of this depleted uranium waste, over 1.2 million tons.
It's currently just stored, but as we'll see, it represents a staggering potential energy source for future technologies.
Our journey started in ancient Greece, and now we arrive at the present day, facing the urgent existential challenge of net zero by 2050. The modern world runs on energy abundance.
We use over 30 times more energy today than we did in the early 19th century. That abundance has fueled almost all dramatic human flourishing. Wealth generation, doubled average lifespans, billions lifted out of poverty.
But 80% of that essential energy still comes from fossil fuels. They are the cause of climate change, and locally, they cause severe air pollution.
Which, critically, ranks as the world's fourth biggest killer, responsible for millions of premature deaths every year. If we are serious about human health and net zero, we have to replace these fuels entirely.
For many, the immediate answer is wind and solar. But they have a fundamental Achilles heel that nuclear power does not, and that is unreliability.
Right. Modern electrified societies require power that is dependable and available on demand, 247. We can't run hospitals or industrial processes based on what the weather decides to do.
So capacity, what a solar or wind farm could make, is a meaningless number.
Generation, what it actually makes is the only thing that matters. Look at wind power. In the UK, a windy country, the average generation capacity factor is only about 31%.
Meaning 69% of the time, the farm is sitting idle or barely turning.
And if the wind stops blowing for days or weeks, which often happens, you need massive backup, which is typically supplied by burning natural gas or coal.
Solar faces even tougher limitations. It only works during daylight, and its output drops off sharply even under minor cloud cover.
In northern latitudes like Canada or the UK, solar potential is poor, and the global average capacity factor for solar remains stubbornly low, often around 12 to 15%.
The real danger here is the energy trap. Over-reliance on intermittent renewables forces us to become even more dependent on burning fossil fuels for round-the-clock backup.
Exactly. Fossil fuel companies recognize this. Shell, for instance, once tweeted, "No sun, no wind, no problem. Natural gas has it covered. Gas is a great partner for renewables."
So the transition becomes less about moving away from fossil fuels and more about optimizing when we burn them.
Meanwhile, battery storage technology is prohibitively expensive and logistically impossible to implement on a national grid scale.
The numbers for grid storage are insane. To back up the UK grid's electricity needs for just a single day would require thousands of facilities the size of the massive Cottingham site, costing hundreds of billions of pounds.
And since weather patterns can remain stagnant for weeks, one day of backup isn't nearly enough. Nuclear power fulfills the requirement for reliable, potent, on-demand, emissions-free electricity.
Beyond reliability, we must address the green lie around mineral intensity and land use.
Right. Nuclear power is incredibly power-dense. A single station, like the Gravelines plant in France, occupies about 1 square kilometer, but can power a city the size of London.
Contrast that with the sprawling land required for equivalent wind and solar farms. The land footprint for nuclear is minuscule.
And we have to talk about mining. Replacing fossil fuels with wind and solar requires a massive, unprecedented increase in the mining of materials like copper, lithium, and cobalt.
And when you measure the rock required to generate 1 gigawatt-hour of electricity, the difference is stark.
It is. Wind needs 160% to 340% more rock mined than nuclear. Solar needs 240% more. This means increased environmental damage from excavation and processing.
And this isn't just an environmental concern, it carries a massive humanitarian cost.
Over 70% of the world's cobalt, essential for modern batteries, comes from the Democratic Republic of Congo. Mining there is frequently linked to child labor and forced labor. Nuclear requires less material and dramatically less mining.
Finally, let's look at the total carbon footprint across the entire life cycle.
While no energy source is 100%, emissions-free energy is always required for mining, manufacturing, and transport. Nuclear is among the cleanest when accounting for its full life cycle from cradle to grave.
And we need to be wary of greenwashing, like biomass, which is essentially just industrial firewood.
Exactly. Burning wood for electricity releases substantial carbon emissions into the atmosphere, often more immediately than coal. Companies receive green subsidies for incinerating ancient forests. Nuclear avoids this type of deceptive accounting entirely.
Now we must tackle the elephant in the room. The two biggest public concerns, which are nuclear waste and catastrophic accidents.
The fear factor is real, but it is often disproportionate to the actual risk. Let's start with waste. The strategy for dealing with it is surprisingly simple. Give nuclear waste to Father Time and he'll turn it into just waste.
This requires understanding the concept of half-life.
Right. Radioactive decay is governed by probability, like a continuous coin flip. Imagine a group of radioactive atoms, each flipping a coin every minute. If they land tails, they decay. Heads, they survive. After 1 minute, half are gone.
The half-life is simply the time it takes for half the atoms in a sample to decay into a stable state.
And when we talk about nuclear waste, we need to break it down. The biggest proportion in terms of volume is low-level waste. This accounts for 87% of all nuclear waste.
But it's only 1% of the total radioactivity. It's things like gloves, contaminated clothing, and tools. Much of it is less radioactive than a banana and decays in a century or two.
The real challenge is high-level waste. This is primarily the spent fuel rods, which are initially stored in deep pools, delightfully called ponds, for cooling and shielding.
And this spent fuel is intensely radioactive because it's full of short-lived fission fragments.
But these decay rapidly. The total radioactivity of the fission products drops by 99.999% in about 400 years. That's still a long time, but it's manageable. Many pubs in England are older than 400 years.
So the complexity arises from the long-lived transuranic elements, atoms, heavier than uranium created during reactor operation.
Exactly, things like plutonium. These decay very slowly, keeping the waste radioactive for 100,000 years, which is roughly the same amount of time Homo sapiens has walked the Earth.
That 100,000-year timeline sounds genuinely terrifying. How do we know that burying it 500 meters down is truly safe?
That's a vital question. The first answer lies in the volume. Despite the long timescales, nuclear power produces a remarkably small amount of waste for the vast amount of energy generated.
Can you quantify that volume? Because 390,000 tons of waste still sounds like a terrifying number.
Here is the boring truth. All the high-level nuclear waste generated globally over 70 years would fit into a single cube just shy of 33 meters across, or inside a modest-sized concert hall.
That small volume is what makes geological disposal feasible. We don't have to manage millions of barrels of toxic sludge like we do with industrial chemical waste.
Right. And the safety of deep geological disposal relies on solidifying the waste into ceramic glass and placing it into multiple, durable barriers deep within geologically stable rock formations, often 500 meters or more below ground.
Now let's tackle the catastrophic accidents that cement the public fear of nuclear technology. Chernobyl and Fukushima.
Chernobyl in 1986 was the worst nuclear disaster in history, but it was the result of a uniquely flawed Soviet reactor design, the RBMK, coupled with rule-breaking operators and corrupt Soviet leadership who covered up the flaws.
The immediate fatalities were about 30 power station workers. Long-term health studies on the 600,000 liquidators have failed to find a definitive, statistically significant link between their radiation doses and cancer fatalities.
The true death toll likely falls in the low hundreds, starkly contrasting with the tens of thousands predicted by questionable early models.
And Fukushima in 2011 provides an even sharper lesson in fear versus reality. It was triggered by a massive earthquake and an unprecedented tsunami.
Crucially, over 20,000 people died in the initial natural disaster. But here is the essential point that gets lost. Nobody died from acute radiation sickness or the ensuing reactor explosions at Fukushima. The reactors failed, but the containment worked.
So where does the death toll come from?
The confirmed death toll linked to the accident itself is 2,314. One death attributed to radiation exposure, and 2,313 deaths caused by the stressful, mandatory evacuation itself.
So the evacuation killed more people than the radiation.
By a huge margin, the evacuation was driven by what experts call undue fear of radiation, which paradoxically killed far more people than the radiation itself.
That really drives home the psychological burden. When measured by deaths per terawatt hour, which is morbid but necessary for context, nuclear power is one of the safest things we do.
Its fatality rate is comparable to solar and wind. Consider a city of 1 million people. If you powered that city using coal, you would expect about 22 deaths per week from air pollution.
And with nuclear.
If you powered that same city with wind, solar, or nuclear, you would expect only 1 fatality every 6 months. The catastrophic impact of dirty air is orders of magnitude more deadly.
Despite the challenges and the historical baggage, the nuclear future is buzzing with incredible innovation, starting with small modular reactors, or SMRs.
SMRs are smaller, simpler reactors that can be factory-built, standardized, and shipped to site. They promise lower cost, shorter construction timelines, and increased flexibility, making them essential for reaching the global goal of tripling nuclear energy by 2050.
And beyond SMRs, we are actively looking at ways to handle the long-lived waste problem so we don't necessarily have to bury it for 100,000 years.
That's where the advanced concept of recycling the fire comes in, using specialized technologies called fast reactors or breeder reactors.
And they use a completely different physical mechanism than the standard PWRs.
Precisely. Think of the neutrons in a PWR as slow bowling balls. They're easy to catch. Fast reactors, conversely, use no water moderator. The neutrons remain fast, moving at bullet speeds.
And these fast neutrons can do two incredible things. First, they can incinerate those long-lived transuranic elements that keep the waste radioactive for 100,000 years.
Right, breaking them down into much shorter-lived fission products. This essentially eliminates the need for geological timescales of storage.
And second, because they use fast neutrons, they can utilize that vast global stockpile of depleted uranium that current reactors can't use.
They turn that fertile U-238 into fissile plutonium-239 while generating power. They generate power and they generate new fuel. That's why they're called breeder reactors.
Speaking of visionary energy, let's talk about the ultimate prize, fusion, sticking light atoms together. The headlines were huge in 2022 when the National Ignition Facility achieved net energy gain.
It was a stunning scientific achievement. They generated 310 watt-hours of net energy, gain enough to boil water for a dozen cups of tea. However, the headlines conveniently ignore the 100,000 watt-hours of electricity required to charge the lasers.
So the experiment consumed 110 times more energy than it generated.
It did. Fusion is the ultimate holy grail, but as the old joke goes, it has been 40 years away every year for the past 40 years. It will not be a deployable solution to the net zero challenge by 2050.
On a much more immediate level, nuclear science is already saving lives right now, particularly in medicine.
Absolutely. Radiation isn't just for diagnostics like X-rays. It is a highly precise treatment tool. Physicians use radioactive isotopes in targeted therapy. Since the thyroid gland loves iodine, they use radioactive iodine-131 to cure thyroid cancer.
But the real cutting edge is targeted alpha therapy.
Right. Alpha particles, those heavy cannonballs, are incredibly destructive, but they only travel about a hair's width. This small blast radius and immense localized potency mean they can obliterate malignant cells with minimal collateral damage.
And one of the biggest breakthroughs is actinium-225. It's legendary because when it decays, it goes through 4 successive alpha decays, delivering 4 destructive hits to the malignant cell.
It's showing incredible promise in treating late-stage prostate cancer. And beyond medicine, radiation has driven incredible advancements in agriculture and ecology.
We have atomic gardening. Scientists expose seeds to control intense radiation, which causes genetic mutations, accelerating evolution. This has led to disease-resistant rice and high-yield barley.
And crucially, the process does not make the plants radioactive. It simply speeds up what nature does slowly.
Then there is the sterile insect technique.
Scientists use radiation to sterilize billions of male pests, like the devastating New World screwworm. These sterile males are then airdropped. Since the females only mate once, they waste their reproductive chance on a sterile male, leading to eradication without harmful insecticides.
Finally, nuclear technology is the only power source that has allowed humanity to truly explore the final frontier, deep space.
Out past Jupiter, the sun is simply too feeble for solar power to work reliably. That's why deep space probes like the Voyager twins rely on nuclear batteries.
These use plutonium-238, which naturally heats itself through alpha decay. That heat is converted into electricity, providing reliable power for decades.
Exactly. And the future of space exploration, including sending humans to Mars, relies entirely on nuclear propulsion. Nuclear rockets are millions of times more energy dense than chemical rockets.
So they can reach Mars much faster, reducing the total time astronauts are exposed to cosmic radiation.
It brings Mars within touching distance, reducing the transit time from months to weeks.
This brings us back to Earth and the global ambition. At the COP28 climate conference in 2023, 22 nations formally recognized the essential role of nuclear energy by committing to tripling global nuclear capacity by 2050.
This declaration suggests that the conversation about net zero is finally becoming serious and grounded in physical reality. As one U.S. official noted, you can't get to net zero 2050 without some nuclear. These are just scientific realities.
We've traveled from the idea of the uncuttable atom through accidental discoveries in Paris to controlled reactions in a Chicago squash court, and then out to the furthest reaches of the solar system.
We've seen that nuclear power is not inherently terrifying, but rather a profoundly powerful tool that offers energy abundance, minimal land use, and a nearly emissions-free path to a cleaner, safer world.
The discovery of nuclear fission was inevitable, just like the discovery of fire. Now we have the moral responsibility to choose what to do with this new flame.
Whether to kindle brilliance for human flourishing and environmental sustainability or ignore it out of undue fear. The global commitment to tripling nuclear energy suggests a serious recognition of this power for good.
And perhaps the most poignant thought of all is that nuclear science has already defined our cosmic legacy. The Voyager spacecraft, powered by plutonium-238, carries a golden record into interstellar space.
And any distant discoverers of that probe will know its origin in time, the 20th century, by measuring the decay of the uranium-238 on board.
Nuclear science has already defined our cosmic legacy. It remains to be seen how it will define our planetary legacy.
Whether we embrace its potential to solve our energy crisis or continue to let fear rule the conversation. But when the rains have washed the temples into the sea, the Voyager twins, powered by the atom, will still be carrying the human spirit through the Milky Way.
Thanks for coming along on this deep dive with us. Remember to follow us on your favorite podcast platform, and see you on the next dive.